Hello everyone, the topic of my presentation today is unified network-based representation of BIM models for embedding semantic, spatial, and topological data. BIM, a digital technology that integrates full lifecycle building information, has significantly improved collaboration and efficiency, leading to its widespread adoption across the construction industry. Despite its advantages, the manual creation and review of BIM models remain inefficient, error-prone, and highly dependent on expert knowledge, creating a strong demand for automated solutions. However, this automation is challenged by the complex and unstructured nature of semantic, spatial, and topological data embedded in BIM models. To address the growing demand for a standardized and interoperable framework in BIM data, IFC was introduced. However, IFC's complex structure and irrelative data for many tasks have led researchers to represent BIM models as vectors of networks. Besides, although IFC provides detailed component descriptions, its hierarchical and semantically rich structure is poorly suited for deep learning, which typically requires structured input. In the meantime, existing vector or network-based BIM representation methods vary widely by task and lack standardization. To address this, we aim to propose a unified network-based representation that retains key information and accommodates diverse BIM models and research needs. We extract and calculate the properties of various components and their spatial and topological relationships. Subsequently, all of these are represented as networks so that we can feed them into the neural network. Specifically, all components are represented as different types of nodes based on their classification in the IFC, with the extracted semantic properties represented as node features. For topological properties, we selected the host and connection relationships contained in the IFC. Host represents the inclusion relationship, where one component is fully contained within another, such as doors within walls. Connection describes the connections between components. Besides, this study introduced a touch floor relationship to describe the vertical connection between components and floors, providing a more intuitive representation of the functional layout and component distribution across different building levels. For spatial properties, this study first extracts the location attributes from the IFC fields, including the local coordinate system and reference coordinate system. However, simple coordinate information alone is insufficient to intuitively reflect the spatial relationships between components. To address this, we define a local spatial relationship by identifying all components within a specified distance from a given component and computing their 5 relative positions, as illustrated in the figure. Then we convert the components, their attributes, and relationships into network. Specifically, all components are treated as nodes in the network based on the classification of component categories in IFC. We treat these nodes into different types, such as walls, beams, pipes, and so on, and their semantic properties are converted into the corresponding node features. The topological relationships are represented as edges connecting the corresponding nodes. These edges are further classified into 3 categories based on the 3 different types of topological relationships. Additionally, the spatial relationships between a component and all components within a local 0.5 meter range are represented as the 4th type of edge in the network. The calculated relative positional relationships between 2 components are used as the features of these types of edge. Our network-based representation method achieves seamless integration with mainstream BIM software by leveraging the standardized FC format as the universal data interface. Users simply need to export the model as FC file and use the proposed program for conversion. A residential floor's overall network are shown in figure. The results show that representing a BIM model as a network effectively simplifies the complex building information and clearly expresses the multidimensional features of components and their relationships, such as semantic, spatial, and topological relationships. Additionally, the introduction of the touch flow relationship and the spatial relationships with a 0.5 meter local range further enhance the network by adding more local relational information. After representing BIM models as networks using our method, they become more suitable for various automated tasks. For example, we can pre-train graph neural networks using strategies like node masking, enabling them to learn and embed implicit design features directly from large-scale and labeled BIM data. Then for specific tasks, we can apply transfer learning with only small label samples, which improves both the efficiency and the comprehensiveness of model checking while reducing the reliance on labeled data. With the advancements of machine learning, particularly graph neural network, structured data formats have become increasingly crucial. Our proposed network-based BIM model provides a structured representation that effectively encodes spatial and topological information. By leveraging unsupervised graph neural network training, our model captures implicit design patterns and complex interactions between components. Even when these relationships are not explicitly labeled, this capability is particularly beneficial for tasks such as design optimization, automated checking, and conflict detection. Specifically, our approach enables downstream application by transforming tasks like automated checking and conflict detection into edge relationship predictions, identifying potential issues based on relationships between components. Overall, the proposed methods enhance the accessibility and interpretability of BIM data, thus facilitating more efficient analysis and reuse of design knowledge. Thank you for your attention.